Welcome to month 4 of the Senior DevOps Engineer track. Over the last 3 months, you've built a solid foundation, production-grade Kubernetes with GitOps, infrastructure as code at scale, and a zero-trust service mesh with mutual TLS. Today we add the reliability layer, the part that answers how well the system is actually serving users and what to do when it isn't. By the end of this session, you'll have 5 real SLOs with multi-window burn rate alerts, an error budget policy that governs release decisions, a chaos suite that tests your hypotheses under controlled blast radius, and an incident response framework, including a blameless postmortem template. These aren't academic exercises. They're the artifacts that separate platforms people trust from platforms people endure. We have 4 hours. Hour 1 is SLOs and error budgets, the theory, the math, and the tooling with Pyrra. Hour 2 is chaos engineering, how to design experiments that produce learning, not theater. Hour 3 is the hands-on challenge, where all 4 deliverables run in parallel. Hour 4 closes with incident response and blameless postmortems, the human side of reliability that most teams get wrong. A note on pacing: the challenge runs concurrently with the session, not after it. While you're working on SLO YAML in Hour 3, the concepts from Hours 1 and 2 are fresh. The incident response content in Hour 4 is the retrospective. You'll see it differently after having worked with the actual SLO machinery. Let's start with the failure mode that motivated SLOs in the first place. You get an alert, CPU at 85%. Is the user affected? Maybe. A service can run at 95% CPU while serving every request perfectly. It just has no headroom. Or it can run at 60% CPU while timing out 30% of requests. Symptom alerts fire identically in both cases. You have no idea which one you're in until you dig. BISTEC Mart had 2 surprise outages in Q1. They weren't actually surprises. The error budget was being burned throughout the quarter. But nobody knew, because there was no SLO. When the next incident pushed the error rate over a threshold the customer cared about, it became an outage. An SLO wouldn't have prevented the incident. It would have given the team a chance to slow down, reduce blast radius, and catch it before it crossed the customer threshold. That's the fundamental insight. An SLO doesn't eliminate failure. It makes failure legible. Before you can define an SLO, you need to know what you're measuring. There are 4 SLI categories worth understanding. Rate-based SLIs measure success fraction, the proportion of requests that are good. Good typically means not a FAFKAX, not a timeout, and not on a path that doesn't represent user traffic, such as health checks, Prometheus scrapes, or internal probes. This is where most services start. Latency SLIs measure how fast the good requests complete. P95 or P99 are the right anchors, not average, because averages hide the tail experience. If your P99 latency is 2 seconds, but your average is 300 milliseconds, 1% of your users are experiencing 2-second loads. For a service with 1 million daily requests, that's 10,000 bad experiences per day. Freshness SLIs apply to data pipelines and caches. How stale can the data be before users notice? A product catalog refreshed every 5 minutes is acceptable. A pricing feed with a 30-minute lag is not. Correctness SLIs measure whether the response was right, not just fast and non-erroring. This matters for financial calculations, recommendation systems, and anything where a wrong answer is worse than a slow one. A common mistake at this stage: picking metrics that are easy to instrument rather than metrics that represent user experience. CPU utilization is easy. Success rate with health path exclusions is harder. Pick the right metric. Once you've chosen your SLI, you need to set the target. This is where most teams make the same mistake. They pick 99.9. because it sounds reliable. A 99.9% target on a 30-day window gives you 43 minutes of error budget per month. That's your total allowance for planned maintenance, failed deployments, upstream dependency failures, and actual outages, combined. A single bad release that takes 20 minutes to roll back consumes nearly half your monthly budget. Compare that to 99.5%, 3.6 hours of budget per month. Enough to run 2.0 downtime upgrades, take a database backup window, and still have 45 minutes for genuine incidents. The difference between 99.5 and 99.9 in engineering cost is not incremental. It's typically an order of magnitude more reliability investment. The right target is the one that matches what customers actually need, not the highest number you can claim. Ask, if we miss this target, does the customer notice? If the answer is no, the target is too tight. Multi-window, multi-burn rate alerting is the Google SRE workbook's most important contribution to this space. Fast burn windows catch acute disasters. Slow burn windows catch chronic degradation. Alerting only on a single threshold at a single window means you'll miss the slow bleed. Pyrra is a Kubernetes operator that turns a declarative service-level objective resource into production-ready Prometheus rules. You define the indicator and the target. Pyrra generates the recording rules for error budget tracking and the alerting rules for multi-window burn rates. The YAML structure is intentionally minimal. You specify whether your SLI is a ratio, success over total, or a latency histogram. You set the target and the window. Pyrra handles the rest. Fast burn alert at 5% of budget consumed in 1 hour, slow burn alert at 10% in 6 hours, and recording rules for the Grafana SLO dashboard. 2 things to be careful about when authoring the indicator. First, your error metric needs to exclude health check paths and internal scrape paths. If health check traffic counts as total requests, your denominator is inflated and your error rate looks lower than it is. Second, for latency indicators, specify the bucket threshold explicitly. And Li of 0.5 for P95 under 500 milliseconds means you're measuring the fraction of requests that completed in under half a second. Tune that threshold to match your actual user expectation. Here are the 5 SLOs you're implementing in the challenge. Look at the targets and notice the pattern. Every target has a business justification, and they're not all the same. The catalog availability target is 90-95%, not 99.99%. A catalog failure doesn't lose money directly. Users can try again. Compare that to the Postgres availability target of 99.9%. Postgres is the source of truth for orders and inventory. A Postgres outage loses money. The higher target reflects the higher stakes. The synthetic end-to-end SLO is the one most teams skip, and it's the most valuable. It exercises the full user visible path from the outside. Your catalog service can be 100% healthy while your storefront is timing out on catalog calls due to a Kubernetes network policy regression from month 3. The per-service SLOs won't catch it. The synthetic check will. Look at the budget column. The catalog availability SLO has 3.6 hours of monthly budget. The catalog latency SLO has 7.2 hours. Those budgets are shared by every failed release, every maintenance window, and every unplanned incident. Your error budget policy governs how that budget gets spent. An error budget policy turns a number, we have 2.1 hours of budget remaining, into a team contract about what actions are allowed. Without a policy, the budget is just a dashboard metric. With a policy, it's a governance mechanism. 4 tiers. Under 25% and burned. Normal release cadence, run chaos experiments, accelerate feature delivery. This is healthy. Warning at 25 to 50%. No risky deploys after 6 p.m. local time, runbook required for any change touching production traffic. Caution at 50 to 100%. Lead approval required for production releases, canary mandatory, high-risk changes blocked. Budget exhausted. 7-day release freeze on the affected service. Postmortem required before the freeze lifts. The override mechanism is as important as the tiers. If a security patch needs to ship during a budget freeze, who can authorize it? If the answer is nobody, the policy will be ignored the first time it conflicts with a real-world constraint. If the answer is the tech lead with documented rationale, it's sustainable. The quarterly review cadence closes the loop. A target you set in month 1 based on a guess about user expectations should be revisited after 3 months of real data. Tightening a target when you've consistently overperformed costs you nothing. Loosening an aspirational target frees up engineering headroom for the next reliability investment. Chaos engineering has a branding problem. The word chaos implies randomness, which implies irresponsibility. The reality is the opposite. Chaos engineering is the most rigorous form of reliability testing precisely because it forces you to write down what you believe before you find out if it's true. The 4 phases are non-negotiable. Hypothesis first. State the specific metric, the threshold, and the recovery time. Not, we think the catalog will be fine. Instead, if we kill 30% of catalog pods, we hypothesize that storefront error rates stays below 1% and pod replacement completes within 60 seconds. That's a testable claim. Blast radius control is what separates chaos engineering from production sabotage. Scope every experiment by namespace, by label selector, and by percentage. Never run chaos against your monitoring stack. If Prometheus goes down during a chaos experiment, you can't observe the outcome. The abort condition is the safety mechanism that earns organizational trust. Before running any experiment, define the metric threshold at which you stop. If catalog 5x rate exceeds 5%, the experiment aborts. This needs to be automated, not a manual judgment call. The most valuable outcome of a chaos experiment is a refuted hypothesis. If everything always works as expected, you're either not running hard enough experiments or your system is genuinely excellent. Either way, learn from the refutation. For the challenge, you're using Litmus, a CNCF graduated project that runs chaos experiments as Kubernetes native resources. The Chaos Engine resource links an experiment definition to a target application. The pod delete experiment is the canonical starting point. You specify the namespace, the label selector for the target pods, the percentage of pods to affect, 30 in the challenge, 1/3 of catalog pods, and the total chaos duration in seconds. Litmus executes the kill, waits, and records the outcome in a chaos result resource. The network loss experiment injects packet loss on the Postgres to catalog path using tcnetim under the hood. You're injecting 10% packet loss for 60 seconds. The hypothesis is that catalog's ritry logic absorbs the loss without burning significant SLO budget. The CPU stress experiment uses stressing inside the target pod, 80% CPU for 60 seconds, enough to trigger HPA scaling and test whether latency P95 stays under 800 milliseconds versus the 300 millisecond steady state. If HPA doesn't scale fast enough, or if a conflicting vertical pod autoscaler is present, this experiment will tell you. DNS chaos is the most underestimated experiment category. Kubernetes services depend on kubedns resolution. Istio sidecars catch DNS, but the cache has a TTL, and applications that bypass the sidecar or perform their own DNS resolution will break. The hypothesis for the DNS chaos experiment: 50% kubedns packet loss for 30 seconds causes no measurable user impact because sidecar caching handles it. This experiment either validates your mesh configuration or reveals a hidden dependency. A game day is not an outage simulator. It is a team training exercise. The system is not the subject, the team is. The reframe matters. If your game day's goal is to find out whether your Kubernetes cluster survives a pod kill, you already know the answer. Kubernetes is designed for that. If your game day's goal is to find out how fast your team detects an issue, how clearly they communicate, and how well your runbook holds up under pressure, you're training for something real. The 5-step game day structure works at any scale. Brief the team the day before, scenario overview, abort conditions, and who plays which role. Run the experiment in a 30-minute window. Call a 5-minute review immediately after, not the next week. Capture the retrospective while memory is fresh. Assign action items with owners and due dates. The hardest part of running game days is organizational permission. Most teams don't run them because they feel they can't afford to break production. The counter is straightforward. Chaos experiments with blast radius controls are safer than random production incidents because you control when they happen, under what conditions, and with the full team watching. The incident will happen eventually. The question is whether it happens with you prepared or not. The challenge puts you in the role of senior DevOps engineer at BISTEC, owning reliability for the Mart platform after 2 Q1 outages. 4 deliverables, 25 points each. Deliverable 1 is the SLO suite, 5 Pyrra YAMLs, plus a SLO doc that justifies every target and lists what's deliberately excluded. The exclusion clause matters. Health checks and internal scrapes inflate your request total and make your SLO look better than it is. Deliverable 2 is the chaos suite. 4 experiments with hypotheses written before running them, and a results document that records what you observed and whether the hypothesis held. At least one experiment should refute a hypothesis. If they all pass, the experiments aren't hard enough. Deliverable 3 is the incident runbook, plus a blameless postmortem template. The key requirement: the incident commander is a function, not a seniority level. Your runbook must be executable by anyone who's been trained, not the most senior engineer on call. Deliverable 4 is the error budget policy. 1 page, readable by a non-engineer, override mechanism named recovery model explicit. The file structure for each deliverable is specified. Follow it exactly. Graders look for named files. Misnamed files are ungraded. For the SLO suite, the synthetic end-to-end SLO is the hardest to write correctly. The synthetic check should test the path that a real user traverses. An HTTP request to storefront, which calls catalog, which reads from Postgres, not a direct health probe to catalog. For the chaos suite, the results document format per experiment requires hypothesis before the experiment, setup commands, observed outcome with metrics, and action items if the hypothesis was refuted. Prometheus query screenshots should be included. It seemed fine is not an observed outcome. The evaluation bands are 90 to 100 for work that could be the BISTEC Mart reliability framework from day one, 75 to 89 for solid work with minor gaps, 60 to 74 for work that exists but covers weak signals, below 60 for work missing the core structure. Passing is 75. 3 roles, separated responsibilities. This is not optional. The incident commander owns the incident from declaration to resolution. They delegate tasks, make calls under uncertainty, and keep the team focused on resolution, not investigation. The incident commander does not debug. They coordinate. If your incident commander is the best engineer on the team, and they're also writing code during the incident, you don't have an incident commander. You have a developer with extra responsibilities and nobody steering the ship. The comms lead owns external communication, status page updates, customer-facing messages, internal stakeholder updates. Their job is to translate technical state into information that non-technical stakeholders can act on. The catalog service is experiencing elevated error rates. Our team is investigating is better than silence, even when the cause is unknown. The Scribe records the timeline in real time in UTC, not around 2 p.m. UTC timestamps exact. The postmortem depends on an accurate timeline. Without a Scribe, the timeline is reconstructed from memory after the fact, and important details disappear. Severity levels govern paging behavior. Severity 1 means customer-facing impact, page immediately, full response. Severity 2 means partial degradation, page within 15 minutes, investigate. Severity 3 is internal or minor impact, next business hours, log and monitor. The declaration threshold should bias to higher severity. If you're unsure whether it's severity 1 or 2, declare severity 1. You can always de-escalate. Under declaring as severity 1, as severity 2 delays the response. A postmortem that names individuals is not blameless. John misconfigured the deployment is a root cause that leads to don't let John configure deployments, which doesn't fix the underlying system gap that let a misconfiguration reach production undetected. The blameless framing reorients to what system condition allowed this misconfiguration to reach production? The answer might be no automated validation, no second pair review requirement, no staging environment that resembles production. Those are fixable system problems. Someone made a mistake is not. The postmortem template follows the SSRE workbook structure. The three-part root cause is the most important piece. The technical root is the immediate cause. The contributing factors are the conditions that made it possible. The systemic gap is what your process failed to prevent. The what would we do differently trap is the most common postmortem failure. Teams answer this question with individual behavior changes. We would have been more careful. We would have tested more. Those answers sound responsible, but are not actionable. The postmortem should produce system changes, automation, process gates, monitoring improvements. If every action item is an individual behavior change, the postmortem hasn't found the systemic gap. An SLO is not a monitoring configuration. It is a team contract. It encodes the agreement between engineering and product about how much unreliability is acceptable, and the agreement between on-call and management about when to stop shipping and start fixing. The error budget policy is that contract's enforcement mechanism. Without it, the SLO is just a dashboard. Your offline milestones extend the work of this session into production. Wire the fast burn alert to Argo rollouts abort rollout, so a bad release automatically breaks. Run a real game day with the actual on-call rotation. Add a synthetic external check from an off-cluster runner. Tune one SLO target up after 30 days of real data. The reading list for this session is 3 books. The original SRE book for the foundational framing, the SRE workbook chapters 1 through 7 for the implementation details, and Chaos Engineering by Rosenthal and Jones for the experiment design theory. Month 5 builds on this foundation. Supply chain security, SBOM generation, SIGSTOR image signing, and policy enforcement at admission. The reliability framework you've built this month is the platform that supply chain security governs.